Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Surya Putra, and I'm from the mathematical physics from class B2. Before I jump in the topic, first of all, I wanna apologize first. This video was uploaded late because my first video was taken down by YouTube because apparently it has background music when I was recording it. So this is re-recorded video so that the that YouTube can just not take down this video. So first of all, I want to address Mr. Sugianto first because as a head of our class in here, so this occasion, I want to uh, explain some of the topic about the topic of the mathematical physics 3 that I already have been intending for. That's it about the fractional calculus. So the problem is, this problem is from Pak Sugianto. So the first problem is actually imagine you ride a roller coaster with a curved track. So in this case, you you are ordered to find the function that can make the track or the train move from the high point of x1 y1 to the x2 y2, which is below fastest in time. So in this case, I wanted to make some of the equations. Uh, so the first of all is, of course, I want to tell you about the uh, is the first. I wanted to show you about this equation first. So, okay, okay. This is the one. So in logical, if you want to shorten the amount of time of the roller coaster, usually to shorten the time, we minimize the distance. So the first of all, we get uh, the the width of the S from A to B is considered as S. So in this case, this knot is actually just uh, abstraction so we can understand it better. But in the reality, from the roller coaster track is not linear, but it's like curve. But how much it's curved, it depends on the functions that we are uh, want to discover. So in this case, to solve the functions or to find the functions, we have to address that in order to get with curve to get the width of uh the area below the functions, we need to uh differentiate, you know, the ds first. So the ds has the component of dy, which is the vertical uh, point, and then dx, which is the horizontal point. So uh with a Pythagorean theorem, we have this differential s square equals to differential x square plus differential y square. So we get the differential s as the square root of 1 plus y prime square dx. So from these equations, first of equations, we get this from substituting the ds with this. And we here we are here to calculate the time, we amount of time that the roller coaster spend. So in this case, we want to we use the velocity because in velocity there are the uh point of the time of it. So in the velocity, we can get the ds per dt, which is in this case, this train is not the, I'm sorry, the frictions of the track and the for the and the force of the from the air that forcing the train up is to being ignored. So we have these energy conservations. So in this thermodynamic laws, first laws, we have this, the total energy of the whole system equals to a total kinetic energy plus total potential energy. So in this case, we have this first state, first positions and the last position, which is the A, and the last position is B. So in this case, these the kinetic one, the kinetic energy, first of all, uh, start from the A, which is in this case there are zero because the velocity, the initial velocity is zero. Plus, in this case, the potential energy is the highest point because the mass, the object is in the highest point in the peak of the height of the vertical positions. So as we know, the potential is the mass times gravitational and times the positions of the vertical point. And then the kinetic energy of the last of the end of the destinations is in P. So in P, in here in P, the kinetic is maximum. So we have these equations of half times mass and times velocity squared. In this case, because there's no height of the train of the carriage of the roller coaster, so in P, the potential energy is equals to zero. So in this case, we can get these equations. dt equals to ds plus square root of 2yg gravitational. So from these equations, we substituting this dt and we integrate it, and the ds we substitute with this square root plus 1 plus y prime square dx. Uh, so in this case, the amount of time is equals to the uh, integral of from x1 to x2 of the square root of 1 plus y prime square per 2yg dx. So in this case, we are calculating of the width of the width of the area below the curve. So like I want to use in computational with numeric method, which is the Simpson's 1 per 3 method to the calculating the total integral from x1 to x2 from the functions. So in this case, I want to show you guys these functions that I have. So this is the functions that I have. Oh, no, not this one. So this is the function that I have. Uh, b minus a per n is equal to h. So I don't want to getting too long in this occasion, guys. So I just jump in right into the coding session. Oh, and then first of all, I actually uh want to make the first equations or the first functions. First functions is the fx equals to 4 times exponential of minus 8 minus 6x. In this case, the the a or the initial or the belowest part of the first part of the x1 is the 0, and the x2 is 0.997. In this case, of course, the I already have the second functions, which is x squared minus 5x plus 4, which I have the exact amount of initial positions, and then the last positions, of course, I have the same as well. So in this case, the first positions of the height is on a 4 meters above the ground, and then the carriage of the roller coaster down into the 0.01 meters. So let's just get into the coding session. Okay, first of all, this is the final term exam of mathematical physics, and my name is Mama Shaya again, and I am currently in the student number of 0.040, and then let's just jump into it. But first of all, let's just define the first functions that I already have. First function, which is the fx equals to, because the fx or the functions is equals to exponential 4 times exponential 4 times exponential of the minus 6x. But in this case, because from the beginning we already have the integral of the square root of 1 plus y prime square per uh, square root of 2yt. So I want to just make this equation to be the exact equations from the integral. So I substituted the y and y prime with this integral, with fx integral. So this is the origin function, the origin functions, and then we have first origin function, and then we have the integral function, the curl function, which is this square root, square root of 1 plus fx or the square root of 2 point y point the gravitational. Yep. So the function is the y. In here, the fx, the f, I will say 0 fx is this fx. Okay, I make this function with these particular functions because my mom actually born in 4th of June. So yes, I love my mom and I want to include her in my activities, in my college activities. So yeah, and then we define the functions of the y equals to fx when the y is, of course, we have the square root of the 1 plus the y prime is minus 24 times the exponential of minus 6 times x, and then we multiply it and we square it. Okay, because this is a matrix, the x is matrix. I have to use the dot uh this dot and the upper. So yes, the multiplier, and then the per of the 4 time the exponentials of the 6 point x, and then we have this, and then we have to input to bring the input of the a or the the highest part, and from the highest part of the y, the horizontal, the vertical, and the positions of the x on the both the highest and the lowest on the vertical conditions. So and the n. In here, I will use the n with 6 PSs. So A is 0, the B is 9.0.9, as we know before from the curve and the n, we wanna have this even number. So I choose 6, which is even. Wait, wait, this is like the n function. N function. Okay, we have the n functions already. And then the functions of the integral functions. Okay, this is a little bit mistake. The functions of integral equals to the I will say it integral Simpsons of the f, a, the b, and the n. And then let's define the h. This is the width of the subinterval of the each bias. So of the each trapezoidal, which is the b minus a per the amount of the bias of the interval, which is 6 in this case. And then we define the e equals to e to the n plus 1. And then I have this x, because x is from the a, the 0, and the b minus a, the h, which is the h, or n, to the b. And then I define the y as the fx. So let's calculate the integral is some times 1 per 3, sorry, 1 per 3 method. As we know before, we already knew the functions or the equations to calculate the integral with Simpson's 1 per 3 method. So that is integral equals to the h per 3 times the y with x1 plus 4 times the sum of the y x of the 2, 2, and n. Yep. Plus 2 times the sum of y x of the 3, 2, and n minus 1. Plus the y of the x of the n plus 1. Wait, this is, I'm not using, I will use the fx. It's easier because I already tried these with y, and my computer doesn't seem to handle it well. So yes, I choose the fx and function. So we have this integral equals to integral Simpsons of the each of the f a and then b and then n, of course, and then the uh integral itself, the actual e, I would say that e is the square root, let's say the square root, uh, 1 per the square root of the 2 times the value of the gravity. So the gravity, I would say in 9.8 meter per second uh, square times the the integral, and then display the value. Mm, so I will say the time span of the roller coaster coaster to reach from, let's say from 4 meters high to the 0.0001 meters below meters with the first functions first function, or I call it the f function is the number to string of the in second. So let's try it. I hope this is working. Okay, I already make a mistake here. Apparently, oh yeah, this is one. This is begin from one to the n plus one. So yeah, and then oh no, we find it. Okay, this is one. E equals to plus one. Eh, yeah, I already for E. Wait. Did I make a mistake? Hmm. Wait a minute. Well, it is actually right though. Mm, let me know this. It's working before, but it's not right now, apparently. So let's try it first. 21 x. What's wrong with this? Parse error near parse error. What is the error? Let's make sure this is not getting smooshed together. This apparently doesn't really look really good. E equals to 1 n plus 1 and 4. Wait, why am I keep getting wrong? So I think I already did this and this is working. I don't know why this is not working again, but apparently this is not working. So I have to figure it out. Hmm. So first of all, it is sometimes it's just like this, and oh, the G and N of 12. Oh, where did I? So it's from this. Where is it though? This is the right. Okay, it's clearly getting. Okay, this is okay. I have this error. I don't know what happened, but this is apparently so serious. So first of all, 21 for n equals to hmm, parse error new line function integral of integral systems. And I don't understand why this is a parse error. Translation. Wait. This is frustrating, apparently. Oh, wait. I already have this. This is like my second functions. This is the second function that I already have. The origin functions is x squared minus 5x minus 4, which is the peak of it, the peak of the height of the y of the fx or the gx functions is in a 4, and the belows is in actually is in 0. But because I want to have the matching uh height of the first equation, so I make it in 0.01 meters. So the a, of course, the a of the first initial x1 is in 0, and then you go from the four meters of the heights come down below because it's a slope. It's not a line linear of the uh purely in y or linear purely in x. So we have this uh compositions of the x and y. So the x is 0 to the 0.997 meters, and the height is from the 4 meters to the below of the 0.01 meters. So yes, this is like the first. I would run this first to see how this is work. So yes, this is working. So the first time of the first time, the time span of the train to reach from the 4 meters to the 0.1 meters with the f functions of the first functions is 0.66962 second. And the second one, the second functions with C functions, the time span of the train to reach 0.01 from the 4 meter is the 0.54124 plus 0.0187 65 E, which is this is the complex functions of the complex number. And then I already uh, compare it. So in here, I'll compare it if the E um smaller or smaller than the E2, which is the E is from the first equations, the F equations, and the E2 is the from the second equations of the or the C. So if the uh time span of the first equations is below the second equations, the function f is more fast in time than c to deliver the carriage from the height of 4 meter to 0.0401 meters. And then the second one, the second conditions is if the time span of E2 below the time span of the functions of f. The truth is, the functions c is more fast in time than f to deliver the carriage from the height of 4 meter to 0.01 meter. So in this case, in these comparisons, we get the function c is more fast in time than f to deliver the carriage from the height of 4 meter to 0.01 meter. So in this case, the first problem, I already solved it, which is the C. We we the problem is to make or to find the most fastest in time of the functions. What the functions that serve the fastest in time, the fastest of the arrival of the roller coaster from the 4 meter to 0.01 meter in time. So in this case, the fastest functions is the C functions, which is the x squared minus 5x plus 4. And then the second questions is to find the slower uh, functions of the C functions, of the functions from the number one. And this time, I find f, the functions f of the function of the four exponentials of the minus 6x, which is uh slightly or is slightly slower than the functions of f in the term of the time span to reach the 0.01 meters from the height of 4 meters. So my conclusion is the fastest functions in this scenario is the c functions, or the I made it as the x squared minus 5x plus x plus 4. And then the slower one, I don't mean it's the lowest, but this is a slower than the c functions. This is the f functions, which is the f function is equals to 4 exponential of the minus 6x. In this problem solving times, I actually, the problem is to solve the first problem is to find the fastest functions could that can serve or deliver the times of the fastest time span of the train to reach 0.01% meters from the 4 meters from the highest peak. In this case, I just find these equations actually because it seems the first see because in my first hypothesis we usually shorten the time we minimize the length or the radius. In this case is the distance or the ds as, which is in my, so in this case this is like the second equations, which is the x2 x square minus 5x plus 5. I have these hypothesis of usually to shorten the time, we usually minimize the distance. So this is the distance we see is curve and this curve. This is the first equations, the f equations, the f functions, and this is the c functions. From the hypothesis that I made before, to shorten the time, we usually minimize the distance, which is in this case is very, very clear that the c functions more fastest than f functions because as the hypothesis that I said before match. As we see here, the curve, the distance is lower, the value of the distance rs is lower than the value of the distance of the track. This track is more likely more uh, long than this track. So my hypothesis and the simulations that I already create in this scenario is match of each other. So I think the idea of variational calculus is to calculate the fastest and the more efficient and more, I think it's not just more uh, or efficient or just more like fastest in this real life because like in roller coaster, this is very, very slow. The slope is very high than this one. So in this one, maybe in my opinion, this one is the curve from the functions f of this first functions is safer uh, to in velocity so that the brake of the roller coaster is not uh, burdened so much. And in this case, because this is so uh, the slope is so high, I think of the burden of the brake from the roller coaster is more likely to be more burden, and I don't think it's safety. I don't think it's like for fun. I don't think that is uh uh efficient. So yeah, but my point is the hypothesis that I make about usually we shorten the time, we minimize the distance, match with the conditions that I make of the roller coaster, of the curved roller coaster with a curved track, which is in here, uh, in parabolic case. This is like parabolic functions. They have a shorten, like shorter distance or the shortest distance from the first one, the f functions, and clearly it makes a huge difference in time arrival or time spent to reach the same exact uh, last positions. So I think this is my conclusion. Okay, let me see. Stop share first. Yep. So that is my solutions to the first problem and the second problem, which is about the fastest time span of uh one scenario with a curve that different. This is like a track, like how we make it fastest, how make we make it efficiently in time span to in reality to bring these equations of mathematical applications in reality, which is this roller coaster is really relate and relevant because yes, in this case, if you shorten the length of the distance, it will make a huge difference on the time span of the first initial positions to the last position that exactly the same of these two functions. So I think that's my conclusions. This is my first and second solving problem of the problem one and first and second. My third videos of the third problem is will upload it after this. So yes, thank you for watching and see you next time. Wassalamualaikum warahmatullahi wabarakatuh. Assalamualaikum warahmatullahi wabarakatuh. Meet me with me again in this is my third problem solving of the third problem. So again, my name is Muhammad Surya Putra and I'm from the mathematical physics of the B2 classes, and now I'm want to try to solve this problem, the third problem of the for the final term of the fourth semester that I attended for. So first of all, again, I want to apologize to Pak Sugianto because this is I uploaded this video late because, as you know, my first video is getting taken down by YouTube because apparently there is a background music when I was recording my first video, and then it get banned by YouTube. And then now I'm re-recording it. I hope you can respect me, respect this difficulty of mine. So yes, I think I'm gonna jump right into it. But before we jump right into it, I have these equations of not equations. This is uh, the problem that we have to facing for. So the first of all, there is a cylinder with a mass of m and have the moment inertia of e of I that can move with a roll without any slip in all the way of the rough surface. So in this case, the frictions from the surface of the cylinder and the surface of the road of the track is ignored, is being ignored. And then this from these equations we can see here, these equations here, there is no anti-force from the the other forces like gravity or other forces like wind, like high wind or something else. So this is purely in harmonic of the spring and the motions of the rolling, as I like rolling of the cylinder. So it's like rotation, radial movement. So from this, we imagine that the core of the cylinder did not give the friction as well. So there is no frictions in the surface of the cylinder and the surface of the track, and then there is no friction as well on the core of the cylinder that attached to the spring. So in this case, we have the K, which is the constant of the spring, and then of course the cylinder here move to the X positive to the right, and then the cylinder have the mass of an m. I'm sorry, and have the radius of the radius of the cylinder is an r. So in this case, it's already equations of the theta, the second theta, second differential of theta plus moment inertia per mass and radius square times theta second prime plus the k, or the constant per mass, times the theta equals to 0. Okay, in this case, I want to jump right into it. Okay, so in this case, I'm gonna solve these equations, or find these equations of the motion functions in with a Lagrangian method, which is we already have, or we already have the topic from the classical mechanics in this semester as well. So the first time we have to look is all the energy that in this system, all energy in the system. So we have the cylinder and the spring. So of course the total energy is from the cylinder that rotational movement, and we have the energy from the spring as well. This cylinder is have two movements. The first one is the rotation movement, and then the second one is the translations to the X positive. So we have the kinetic translations and the kinetic of the rotations of the cylinder. So this is, we have is equations. So the kinetic is T equals to kinetic translations, which is the half and the square, and then we have the translations. The translation kinetic is half moment inertia times the omega, or the angular velocity, quad square. So we know in this case, because we are being asked to make this in a theta, we need to address the phi in a theta as well. So in this case, the phi is omega square times the radius square plus this is, and then the omega, we change the omega into a theta. So because the omega is the first differential of a theta to the times, right? So we can write it as E theta prime square times r square plus the rotation energy, which is of course the same. The omega is theta prime square, and then we have the theta prime square, so we separate it, which is becomes this one. So if you want to separate the half, of course you can, like this one. So we have this one, these equations, and then we look at the another energy, which is the potential. In here, the rotations don't have any potential energy, but the spring, of course, as you know, have the potential energy, which is the minus half kx square, which is in here the x can be denounced as the theta r square. So we have these equations in here, and then we now arrive in Lagrangian method. So Lagrangian is of course the kinetic minus the potential. So we have the kinetic energy. This is the kinetic energy, and we already know the phi, or the potential energy. So this is the mr square plus e times half theta prime square minus the potential is half k theta square and r square. So we have these equations of Lagrangian, and then we get into the equations of Lagrangian. So the Lagrangian is the first differential of the Lagrangian with theta prime, and then we differentiate again with respect of the time. So then we minus it of the first differentials of Lagrangian that respect from the theta. So first of all we differentiate the Lagrangian function with the theta prime. So we have this theta prime is to, in this, the differential of theta prime is to theta prime square is to theta prime. So we already have this
mr square plus e times the theta prime. So and then we calculate or we differentiate the second part. This is the first differentials of Lagrangian functions with respect to the theta. So we have the half of the k r square with 2 times theta. So we already have the kr square and times theta. So we substituted with the first that we already know, the equation Lagrange equations, which is this d per dt of the dou Lagrangian per dou of theta prime minus dou Lagrangian per dou prime of the theta, so equals to 0. So in this case we already have this. The first differentials of the dou Lagrangian per dou theta prime is mr square plus e plus I times the theta second prime plus kr square times the theta. So we have these equations of the motions, the equations of the motions of the functions of motions is 1 plus e per mr square times the theta second dot or second prime of the second differentials of the theta plus k per m, so this equals to 0. So this is, we already have the this. So we conclude that this is the final. So the problem is to get the evidence or the proof that these equations is the same as the equations of these equations. And yes, we get the same exact equations. So my conclusions is the problem is solved and the equations is proved to be true. Okay, right now, because this is the last time or the last video that I already recorded. So first of all, I want to thank you to Pak Soegi about all the insight that I have that Pak Soegi gave to me. I already appreciate that so much, and this is actually my last meet of you in this semester. So yeah, hope you enjoyed it and hope you can have can give good and objective and generous the point in my transcriptions. So yes, before this I think this is the last, and thank you for having me, thank you for listening to me, thank you for watching this video. Akhirul Wassalamualaikum warahmatullahi wabarakatuh.